Hi everybody, welcome back. We're going to talk about linear transformations with me. Today, the big idea is we want to be able to view matrices as functions. Now that might sound a little bit weird, but we're going to say that A is an M by N matrix. Then we would have like X would be in Rn if we wanted to do A times X. So A we would then think of as the input, or X would be the input, sorry. So then A times X, which is the output, is in Rm. Okay, so thus we can think of A as being a function from Rn to Rm if, let's see, we denote it by like T of X being A times X. This would be the function version. Okay, so here we go. We have our nice definition. We have a transformation, or we can call it a mapping or a function, T from Rn to Rm is a rule that assigns each vector x, where x comes from Rn, to a vector T of x in Rm. And we denote that with this function notation. T goes from Rn to Rm. Okay, and we've got some definitions to go with our function. So actually I'm going to be nice to have this sitting right here. So it goes from Rn to Rm. There we go. So the very first one is domain. So basically stuff that you put in. So that side is domain. And then the stuff that comes out, so where things land, is going to be the codomain. And then if you put something into our function, the output is called the image under the image of that vector under T. And then if you take all the things that you get out of it, we call the set of all of them the image of T. And then lastly, we've got an M by N matrix A, and we call the transformation from Rn to Rm, we call it a matrix transformation if we can write it this way, which is what I wrote on the previous page. Okay, so while this is a different perspective than we've previously thought about it, we can still use the tools we've already developed because they are equal and we know things about A times X. So for instance, we're going to try and answer this example. We have T goes from R4 to R3, and we have T of X is equal to A of X, and all we need to know is A, and then we know everything that we need to know about T. So first question is we want to find all the X's such that T of X will be equal to 0. So we are looking for, let's see, I like blue. We're looking for T of X to be equal to the 0 vector. That means we need A of X to be equal to the 0 vector. So we need to find the X vector such that this is true. We know how to do that for A of X. All we have to do is set up an augmented matrix. So let's do that really quick. And then we've got 0, 0, 0 on the right-hand side. Okay, so if we do R3 minus 2R1, we can have 1, 0, 0, negative 4, 1, 2, 7, negative 4, negative 8, negative 5, 3, 6, 0, 0. Okay, sorry, I was a little bit bad. I didn't do it row by row. I'll do this one row by row. Okay, so we've got R3 minus 2R2, so that we can get rid of this 2 right here. Row 1, row 2 stay the same. And then for row 3, we end up with all zeros. So then we have free variables. Which ones are free variables? Okay, and then I'm going to go ahead and do R1 plus 4R2 so that we can have reduced row echelon form, which is my favorite personally. So 1, so that's going to be a 0, 16 plus 7, no, 16 minus 7, it's negative 9, and then 12 minus 5, 7. There we go. So then we can say x1 minus 9x3 plus 7x4, x2 minus 4x3 plus 3x4, oh, they're equal to 0. x3 and x4 are free. And then that means we've got the x vector is equal to, we've got negative 9x3 plus 7x4, x2, oh, not negative, not negative. You have to flip. Sorry, because this equation here, you have to move the x3 and the x4 to the other side. So x1 would be 9x3 minus 7x4. And then for this one right here, we've got x2 is 4x3 minus 3x4. And then we have x3 and x4 by themselves. And then remember, we want to split this up into two different vectors. You've got the x3 vector and the x4 vector. And if we do that, we're going to have 9, 4, 1, 0 for x3 plus negative 7, negative 3, 1, 0 times x4. And then what's another way we could think of this? We could think of it as the span for these two vectors here, if we really wanted. But we're going to go ahead and we're going to stop here for our solution. Okay. Next one we want to know is this vector in the range of t. That is the same thing as asking, well, does this vector ever get mapped to? So then, does this ever happen? That would be the same thing as asking, does this ever happen? Well, we can figure that out. We can use augmented matrix. So let's go ahead, let's write that down. So we've got 1, 0, 2, negative 4, 1, negative 6, 7, negative 4, 6, negative 5, 3, negative 4, negative 1, 1, 0. And we're going to start off with R3 minus 2, R1. Again, that's going to be 1, negative 4, 7, negative 5, 1, because row 1 stays the same. 0, 1, negative 4, 3, 1, because row 2 also stays the same. And we are left with a changed row 3, which is going to be 0, 2, negative 8, 6, 2. It is probably good practice for you, by the way, to like pause this video when I do these Gaussian eliminations really quickly and try and do the row before I do to make sure that you're doing it correctly. Okay. And then next we want to knock out that 2 again, just like last time. And so we have row 1, row 2 stay the same. And then row 3 gets knocked out completely. Okay, so then we are left with pretty much the same matrix as before. I'm gonna scoot him a bit. Oh. Give myself enough room to do the last one, which is R1 plus 4R2. So then row 3 stays the same. Row 2 stays the same. Row 1 is going to change. Let's see, that was, just double checking myself, negative 9, 7, and so then that's going to be a 5 over here. Okay. So then, is that a 5? It is not a 5. I've dropped a negative. So this is a 3. I dropped the negative here and here, by the way, but I put them back in. Okay. This is what I'm expecting. So then we've got x1 minus, you know what, I'm going to, I can't ask you if I can go quick. I'll go slow. So 7x4 is equal to 3. x2 minus 4x3 plus 3x4 equals 1. x3, x4 are both free. They're little free little bunnies. And so actually, we could stop right here. I asked, is it in the range? And very obviously, we're going to get a good solution from here. And so like, I could say, yeah, it's obvious now and leave. But I'm going to go ahead and I'm going to take it all the way. Let's rewrite this real fast. We've got x1 equals 3 plus 9x3 minus 7x4. x2 is 1 plus 4x3 minus 3x4. x3, x4 are both free. So then our solution vector x would look like, and I'm going to do this one fast. So we've got the normal part with no x's attached, so 3 and 1. And that means this vector will be 3, 1, 0, 0 times no x's, then plus, and then this is a little bit of a review, plus the part, that's the particular solution, and then we can just add on the homogeneous solution. And then plus, this is a 1, maybe, negative 7, negative 3, 0, 1, x4. And I'm checking, I did that wrong on this slide. There we go. Okay, So we have found such a vector that exists. So then it is in the range. It being the vector. I just didn't want to write it out. Okay. So now I want you to recall some properties of matrix vector multiplication. Remember, we had this first rule where you can distribute, where's my highlighter? There we go. You can distribute a matrix over two vectors, and then you can also pull a constant times a vector. You can pull that constant out to the front. Since that holds for A times, or matrices times vectors, that means it should also hold for linear transformations, because linear transformations are also matrix transformations. So here we go, or not linear transformations. I got ahead of myself, I'm sorry. It should also hold for matrix transformations where T of x is equal to A of x. So it's got to hold for those T's. And in fact, we have a name for that. I totally spoiled the surprise. Definition 3. We call it a linear transformation. It is not just a matrix transformation. It is a linear transformation if it satisfies the two properties that I listed up above, but in function form. And then we've got some algebraic properties that fall out from that I can go ahead and prove for you really quick. So if you have a linear transformation and you've got 0 as your input, then 0 is going to be, I see that algebraic properties of linear transformations. And I will change that on the notes. That way, when you have blank notes, that's correct. So T of 0 is equal to 0 always. The reason for that being, let's have U be in Rn. Then if we have 0 times U, you're going to get 0. And then there's someone at my door, so I'll be right back. So if 0 times U is going to be 0, let's go ahead and try and figure what T of 0 is going to be. So then T of 0 is going to be equal to T of 0 times some U. It doesn't matter what U. And then we get to use this property right here, number 2. And we can say that 0 times T of U. We get to pull that 0 out to the front. And then 0 times anything is 0. And so we're done. Property 1. Property 2, we're going to use some of the above things that we just discussed in definition 3. So we've got T of CV plus DU. And we can break that sum up by property 1. We can say T of CV plus T of DU. And then we can pull those constants out to the front by the second property. And there you have, we've proved part 2. Okay, what I'm not going to do is I'm not going to do 3. All you have to do is you have to repeat what we did for 2, like p minus 1 times. Okay, so next on our list to discuss is the matrix of a linear transformation and some geometric examples. So my question is, matrix transformations are examples of linear maps, but are they the only ones? I'm going to say, well, nope. Let's do definition 4. So the jth standard basis vector in Rn is denoted by E sub j, and it is the jth column of the identity matrix. So reminder, identity matrix looks like this. We've got ones on the diagonal and zeros literally everywhere else. So what I'm saying is E sub 1 would be this first column here. And E sub 2 is the second column, all the way up. I don't like that 0. To E sub n. So that means we could write the identity matrix using these basis vectors, or standard basis vectors. So that means for the jth one, just to illustrate what he would look like, is you can have zeros all the way up to this only one that's going to show up, and that one is going to be in the jth row. How is that helpful? Well, let's consider an arbitrary matrix with arbitrary entries. We can split him up so that each entry has its own vector all the way up to the nth one. And then we can factor those x's out. So what vector did I just write? That's the E1 vector. And then I'm going to skip up to xn because I'm lazy. There we go. And this is the En vector. So all in all, we can write it as x1 times E1 plus x2 times E2 plus xn times En. There we go. So then that takes us to our next definition or theorem. We have T is a linear transformation. It can be expressed as a matrix transformation as long as T of x is equal to A times x. And the columns of A are going to come from plugging in those standard basis vectors into T. So column 1 is found by plugging in E1 to T, and column 2 would be plugging E2 into T. We're going to have a quick vocabulary moment. We call A the standard matrix of T. So that means we can express, this theorem is going to let us express any linear map as a matrix map. For instance, let's do a couple of examples where we see this happen. We've got T is going to map from R3 to R3, and we want it to be the projection onto the XY plane. So to demonstrate, here's our axes, x, y, and z. If we have a vector, then we could say that he is being projected down to the xy plane like this. So then that would be the projection. So we would put in this matrix or this vector x, and we would get out T of x down here on the xy plane. So what do we want to happen? Well, what happens component-wise? What happens to the x component? Does it change? No. The x component of the matrix that we put in, or the vector that we put in, is going to be the same as the x component for Tx. So that means we can write it this way. So if we have 1, 0, 0, 1 would be the x component. We don't want him to change. So we will do exactly that. He does not change. What about the y component? What happens there? Y doesn't change either. The only thing we're going to change is z. We want to eliminate the z component. We want to push it down onto the xy plane. So y stays the same. So then what happens to the z component? We basically just want to get rid of them. So that's what we're doing. No z component. And then we take these guys and we can construct our matrix A. So the very first one is our first column. The second one was the second column. The last one was the last column. There you go. This matrix will take any vector in R3 and project it down to the xy plane. Some more examples. These examples are going to be in R2. We're going to map from R2 to R2. For instance, we are going to reflect over the x-axis. So let's say we have this vector x. That means t of x is going to be down here. There we go. So what happened to the x component? It stayed the same. What happened to the y component? Well, he became negative. He went from being up to being down, which means he's the exact same value, just negative of what he was before. And so that's what we do here. So then we take these together, and you get the matrix 1, 0, 0, negative 1. And that matrix will take any vector in R2 and flip it across the x-axis. Last one we want to do is we're going to have a matrix that is going to scale a vector vertically by a factor of k. So if this is x, we want to scale vertically by a factor of k. So that would basically mean if k was like 2, we would want to double where we end up. We do not want to change the x component at all. We just want to go up twice as high as we were before. So then how do we decide on what a is? We take the x component and we say what happens? Nothing. He stays the same. We take the y component. And what do we say happens to him? He gets multiplied by k. And then remember, we can distribute that to each component in a vector, so it's really just 0k. So that means a will be 1, 0, 0k. Okay, last example for today. We're going to talk about the rotation matrix. We want to take a vector and we want to rotate him, that's bad, around the axis by theta. So again, we're going to do this component-wise. So for the x component, let's say we have just E1, right? That would be the point 1, 0. If we wanted to rotate him by theta, he would end up looking like that. So this would be T of E1. How are we going to figure out where it's gone? Easy. We have the power of trigonometry, right? You guys all loved trig. We can turn this vector into a triangle. We know its hypotenuse is 1 because we started with E1 and the length of U1 is 1. So how do we find the opposite side? The opposite side is sine of theta, and then the adjacent side is cosine of theta. So then we can say that t of E1 is going to be equal to the x component is now cosine of theta, and the y component is now sine of theta. Okay. Y component. What happens here? Well, let's say we have E2, which is going to put us on the point 0, 1. We're going to rotate it by theta. There we go. We can still do a triangle. We're going to do that triangle right there. So what angle is inside? Remember, we have a right angle here. And so the angle inside is going to be pi over 2 minus theta. Hypotenuse is 1. So then this side, the opposite side, is sine of pi over 2 minus theta. Oh, that is hard to read. It's a little bit better. Okay, and then we say the adjacent side is going to be cosine of pi over 2 minus theta. And then maybe a few of you caught this, it should be a negative cosine because we are on the negative axis. So now we can say that t of E2 will be x component is negative cosine pi over 2 minus theta, and then sine of pi over 2 minus theta. And then I'm going to ask you to remember what cosine of pi over 2 minus theta is. Remember, cosine and sine are offset by a shift of pi over 2? Question mark? Asking you to remember a lot here. But hopefully you can accept this enough to be like, oh yeah, if you shift a cosine by pi over 2, you get sine. And then if you shift sine by pi over 2, you get cosine. If you don't believe me, just go plot those really fast. Okay, so then A is equal to cosine theta, sine theta, negative sine theta, cosine theta. And then to prove that it works, don't take my word for it, I've got some Mathematica to play with. So here we go, we've got vector v. We've got a lot of code sitting in here. I'm going to highlight what's important. We've got vector v, and then notice inside this manipulate is what lets me have like this thing here, this bar, and a lot of other things, like I have my arrow, but the important part is I'm telling the arrow to go from the origin 0, 0 to this point here, which is very long. It's a very long point because I've got cosine theta, negative sine theta. This is row 1 of A. And then we have sine theta, cosine theta, which was row 2 of A. And then we're going to multiply that by any random vector v. And I decided on 2, 1 because that's what I typed in. So you take theta and you move it, and it's going to move your vector around the circle. And so if you want to play with different vectors, you can come here. For instance, I could have made that like a negative or something. And then you just hit Shift Enter or reevaluate the cell, and it'll update this plot right here. And you can send your vectors around the circle however you want. Okay, but that's all I've got for right now. I'm going to encourage you to go and read your book go look at the pictures in section 1.8, tables 1 through 4. They have a lot of good pictures that go with the matrices, and it's really cool to look at. Try and understand some of those matrices. It'll be good for you. I don't tell you to go look at your book much, and so hopefully you're like, oh man, maybe I should really do that. So yeah, I'm gonna get up and go ugh for a moment and come back and record part 2. I advise you also do the same, and I'll see you in a minute. Bye.